Okay, let's go ahead and do a demonstration of the photoelectric effect, which is the emission of electrons from a metal by just shining light on it. So I have here an electroscope, which is just a device that can hold some static electricity, some electric charge. And I can apply the charge by just scraping it on this piece of metal at the top, which is a piece of magnesium. So let's go ahead and use just some wool and a plastic charging rod, create some static electricity, scrape it on there, and you'll see that the charge is stored on the device. How do I see that? Well, there's a piece of foil attached to the main electrode, and it splits, and since it's the same charge on the metal and the foil is also metallic, like charges repel and then pushes apart. So you'll see that there's charge stored on the electroscope by putting a charge. But if I provide a way for the charge to come off, for example, if I touch the metal, I will provide a path to ground, and that'll remove the charge. So the charge is removed. Right, so I can apply charge here. The foil is moved off horizontally to the right, but if I touch it, charge is removed because I provided a path for the charge to go. But let's put the charge back on. Go ahead and scrape it and put it on the magnesium. And let's go ahead and shine some light. Here is a flashlight, right? So I can turn that on, obviously a light, shine it on the magnesium. All right, is the charge still on there? Oh, yep, still is. Well, that's rather silly, isn't it? Because obviously I have lights on in this room, and that light is not removing the charge off of the magnesium. So what's going on here? There must be some dependence on the wavelength of the light. So I have over here an ultraviolet light. You might know it as a black light. And I can turn that on, and you may not see that because it's ultraviolet. And we will go ahead and shine it on the magnesium. Okay, did anything change? Let's see. Oh, indeed, where'd the charge go? I didn't touch it. Only the light was shined on the magnesium, but the charge bled off. Somehow the light caused the electrons to kick out of the metal. That is the photoelectric effect. Okay, let's look at that a little bit more closely. Let's provide charge onto the electroscope, as there. And let's go ahead and shine the ultraviolet light on it. Okay, I can do that again. In case you missed it, scrape it on there, foil is charged, turn on the black light, the ultraviolet light, which by the way has a wavelength of 254 nanometers, shine it on the magnesium, the charge is removed. And indeed, yes. Okay, but regular light did not do it, so maybe it depends on the wavelength. And it turns out I have 3 ultraviolet tubes. I have one that also has a wavelength of 302 nanometers. Let's go ahead and try that. All right. Oh, I should turn on not only the light, but add some charge. So let's go ahead and charge up the electroscope. There we go, got some charge on there. 302 nanometers. Shine it on the magnesium. Don't touch it. And was the charge removed? Not yet. Let's try that again. There. Now it's removed. Okay. So 302 nanometers is enough to do it as well. So let's put some charge back on there. Make sure to aim the light now at the magnesium. So we've got some charge. But now I'm going to go to 365 nanometers. I have another dial here. I can switch it to 365 nanometers. Put that on. All right. Now let's be careful. Let's make sure I shine it on the metal. I can bring it even close. All right, did the charge remove? Doesn't look like it. 365 nanometers did not remove the charge. Let's go back to 302, right? Let's go back to 302, make sure I did that right. All right, we're at 302 nanometers. Let's shine it on the metal. Oh, it was removed. It's not a fluke. So there's a cutoff between those two wavelengths. All right, can we understand that cutoff in the photoelectric effect? Well, it turns out magnesium has a work function of 3.7 electron volts. What does that mean? It means the electrons are bound. They have a binding energy of 3.7 electron volts in the metal. I have to add that much energy to each electron to kick it out. Well, Einstein proposed that light was quantized in the photoelectric effect, and each photon has a certain energy, which you can calculate from the wavelength. I leave it to you to figure out that calculation, but I will tell you the answer. So at 254 nanometers, the energy per photon, each particle of light, is 4.9 electron volts. And that is safely above 3.7, the electrons are kicked out. At 302 nanometers, you're going to get less energy per photon. It's 4.1 electron volts. Well, that's still above 3.7, so electrons are kicked out. At 365 nanometers, the energy per photon, you can calculate this, is only 3.4 electron volts. Oh, that's less. That is not enough to kick out the electron. You might get them a little bit excited in the metal, but they are coming out. So it requires wavelengths that's sufficient to have enough energy per photon to kick out the electrons. That energy, that work function, does depend on the type of metal. I'm using magnesium here, but other metals have different values. And you can study that and determine the exact wavelengths that you need. Okay, that ends our demonstration of the photoelectric effect.